Hi, Mr. Bradbury. This is my group's two experiments for the mass spring and the pendulum. My group is Brandon, me, Orlando, and Lauren. And this is what you're going to need to recreate this experiment for yourself. So you're going to need a sturdy base to either support the spring system or swing the pendulum. You're going to need different masses. They could be 5 grams, 10 grams, 100. Our group used 100 and 200 grams. You're going to need fishing wire to either tie the pendulum on or to tie the spring to the base. And that's really all you're going to need to do this.
To set up a mass spring experiment, you have to have materials such as a strong base to keep the weight and string still. Fishing line is preferred due to how strong and invisible it looks. Use weights measured in grams and in varying sizes. Tie the fishing line tightly onto the spring so it doesn't wobble. Be careful that how strong the spring is. It's possible for having a spring that's too strong to be unable to have any displacement within.
Mass spring system. In our mass spring system, we have a mass hanging from a spring. When a small force is applied to the mass downwards, gravity expands the spring, moving the mass in the vertical direction. In this lab, we will conduct 4 experiments with 3 trials each. In each experiment, we will change the masses to 0.1, 0.2, 0.3, and 0.4 kilograms. We will use the equation F spring is equal to Kx to calculate the strength of the spring in each trial. To find the maximum and minimum points of the spring, we will use a slow motion camera. We hypothesize that the greater the mass, the displacement of the spring x and the period t will increase.
So, for our calculations in the mass spring system, we started with finding x. And to find x, first we measured the unstretched length of the spring, and then we measured the stretched length of the spring, and subtracted the stretched from the unstretched to find a final x. And then we plugged that x into the formula F equals K of x using mg as the force F, and calculated our K. And then we used our K and plugged that into the formula period equals 2 pi times the square root of m divided by K. And then we found our period. And at the end, we did 4 experiments with 4 trials each. And we averaged everything together at the end of each 4 trials to find 1 K, 1 X, and 1 period.
This is our conclusion to our mass spring system. We hypothesized that K and T would change as the masses changed. We were correct in this assumption, but our experimental values did not reflect the theoretical values we acquired. With a 99% error, we figured this out because our X values were much harder to measure with the smaller masses, giving us a higher K value. What we could have changed to fix our margin of error is we could have redone the experiment with a stronger spring, which would have made it easier to measure due to less movement. We also could have been more precise with our measurements. This could result in a smaller margin of error.
In our pendulum experiment, we hypothesized that mass will have no effect on period, and amplitude would not have effect on any of the other variables. In this part of the lab, we created 2 pendulum experiments. We will measure the amplitude and period while changing L and M. We will start with an angle at 140 degrees for both experiments. In the first experiment, we'll have a string of 0.032 meters with masses 0.1 kilograms, 0.2 kilograms, and 3 trials each. In experiment 2, we will do the same, except the string will change to 0.02 meters, and the masses will continue to be the same. To find period, we used 2 pi times square root L over G to find period. And then we used force equals to mg sine theta to find force. With that, we were able to use amplitude to find amplitude and
Pendulum. To create our pendulum, we tied a string to a base. We then tied our mass to that string, so that the mass was off the ground. To have a consistent angle for our experiments, we taped a protractor upside down to the place where the string met the base. In our experiments, we changed the masses and the length of the string.
These are the calculations for our pendulum experiment. We actually need to use 2 equations, which is T is equal to 2 pi over times the square root of L over G, and F is equal to mg times the sine of the angle. Because we did 2 experiments with 6 trials each, we're going to use the average of all the trials for the final numbers. In experiment 1, t was equal to 0.35867 when the length of the string was 0.037 meters. Mass actually does not affect t in any way. In experiment 1, F was 0.6305 newtons when the mass was 0.1 kilograms, but when the mass was doubled, F also doubled to 1.261 newtons. When finding F, the length of the string does not matter at all. In experiment 2, T actually went down because we reduced the length of the string to 0.0185 meters, and T shrunk because it is only 0.2727. Again, the masses does not affect T, but because the masses were the same in experiment 1 and experiment 2, the forces of the pendulum did not change.
In the end, our hypothesis was correct of how mass, m, has no effect on period, t, and amplitude, a, including how amplitude had no effect on anything and just based on length, l. Things that could have been different would be having a more sturdy base, which changed how we calculated period. We also could have swung it at a more horizontal angle to have a more precise period calculation.